This video is about the marching cubes algorithm that's used to visualize volume data. Volume data, also known as voxel data, is a series of values spread across a grid, typically in 3 dimensions. Volume data is encountered in many different cases. In measurements, for example, in medicine, MRI or CT scanners generate information about the composition of the body, and being able to visualize that data is critical for medical professionals. In science and engineering, complex equations often are evaluated over a grid, resulting in volume data. For example, and the reason that I became interested in this topic is in the calculation of molecular orbitals, that is determining where you might expect to find electrons within a molecule. And in graphics, complex equations can similarly be evaluated across a grid, but for artistic purposes, such as those employed in method balls. For this video, I have some example volume data that we can have a look at based on molecular orbital calculations for caffeine. So, switching to the terminal and starting Python, I have version 3.10. We can import NumPy and then check with numpy.version.version. We have 1.23. The volume can be loaded with the numpy.load method using testvolume.npy file name. Looking at the volume, we can see that there is much more information than NumPy would like to display, hence all the ellipses. If we really want to see it all, we can type numpy.set print options with a threshold of numpy.inf, and now it takes a little bit longer to show us. We can see this large amount of information, far too much to visualize. In fact, we've got a volume of shape 111 by 98 by 64, which, using the .size attribute, is just short of 700,000 data points. And it ranges from maximum of 0.35 to minimum of minus 0.34. We can start to consider this data if the volume is represented by a box of size 111 by 98 by 64, then what we can do is draw a sphere at every single one of the points within that volume. And as we fly through this, we can see just how much information this is. Far too much to comprehend. But if we shade the information according to positive or negative, and then scale them according to their values, some useful information starts to emerge. The marching cubes algorithm offers an alternative approach that's much easier to draw and appreciate. The algorithm calculates a surface within the volume that encloses all the points that cross a certain level, or an isosurface. It's called marching cubes because we're going to split the volume into individual unit cubes and consider each cube by marching one by one to build up the geometry. So if every location in the volume has an x, a y and a z coordinate, the cubes we're going to consider are between x, y and z, and x plus 1, y plus 1 and z plus 1. Switching to the editor, we can start by importing NumPy, and if name equals dunder main, we will load the volume using numpy.load and testvolume.npy, the same as before. We can print a message, volume loaded with shape volume.shape. Okay, let's see what happens if we run this. And it looks like our volume loads okay. So we want to find an isosurface at a particular level, and for this data, level equals 0.05 works well. And we can print processing volume at level. So what we need now is to define a function that we can call marching, so def marching, that takes a volume and a level, let's default to 0, and that's going to generate some vertices, which will initialize to an empty list, and also some triangles, also will start with an empty list, and then we're going to return these values. And so we can call this function by writing vertices, comma, triangles, equals marching, volume, comma, level equals level. And let's print our marching function resulted in len vertices, and len triangles, found. Again, let's just have a sanity check. And it works, and obviously we don't find anything because we haven't started yet. The first thing we need to do in our function is to compare the volume to the level. So we can define volume test as a NumPy array where the volume is greater than or equal to our level, and with a Boolean data type. We only care for most of our calculations whether or not our value is above or below the level, so we're perfectly accommodated by the Boolean data type. We need to evaluate the volume across its 3 dimensions. So we'll enumerate the volume for z in range, and we can get the dimensions from the column dim x, dim y, and dim z. We can get them from the volume test.shape attribute. And so we'll do volume for z in range dim z minus 1, and then y, and then x. Noting that the marching stops just before each of the edges because we need 8 corners to define our marching cube, and that we do the x as the most rapidly changing of our x, y, and z. Although this doesn't matter, and it's important to remember that we can do this algorithm in any order. So what we need to do now is to check where we need to draw a vertex. And so we need to see where our volume crosses the level. And every time that happens, we need to draw a vertex. And we can do that simply by checking if our volume test at our current location, x, y, and z, is not equal to the volume test in one step in the x direction, then we need a vertex. So we can go vertices dot append and then x, y, and z. We know the vertex lies at the y and the z, and we also know it lies somewhere between x and x plus 1. So if we call that delta, and then we can calculate delta by interpolating, so we'll write interpolate, and that's going to be a function that takes the value of the volume at our current location, x, y, and z, compares it with the volume at x plus 1, y, and z, and also the level. So we need to define an interpolate function, def interpolate, and that takes two values, a and b, and the level. The first thing we're going to do is just zero these values. So we'll do a equals a minus level, and b equals b minus level. And we'll do a linear interpolation. In this case, we just return a divided by brackets a minus b. There are many different types of interpolation, and Wikipedia does a great job at summarizing them. Linear interpolation is good for us because it strikes a balance between simplicity and effectiveness. And our equation here is particularly simple because we zeroed the values to the level and because x was in the range from 0 to 1. Okay, so and I'll just add an extra space. So I said that the order of which we process the vertices doesn't matter, and that's true because we will assign each vertex a unique ID. Every single vertex is found along the edge of one of the marching cubes. So we can come up with a unique vertex ID that will depend upon our current coordinates x, y, z, along with a direction that represents the direction of the edge. So we can vertex IDs dot append, and we'll initialize an empty list at the top of the function, and we will calculate the vertex ID based upon x, y, z, and our direction. We're doing x, so we'll do direction x, and we can define this at the top of our document. So we'll just have direction x equals 0, then we can copy that for y equals 1, and then z equals 2. Okay, so let's define our calculate vertex ID function. We'll do that within the marching function, and this will take our x, y, and z along with our direction with a small d. And to get a unique ID based upon location, we need to return the x plus the largest possible y, which is y multiplied by dim x, plus z multiplied the largest possible y, which is dim x times dim y. And we can define dim xy, which is just dim x times dim y, to tidy it up a bit. Now we have three directions, so we need to multiply this number by 3 and then add the direction. So now what we can do is explore this in the other directions. So let's copy and paste, switching x plus 1 for y plus 1. Again, x plus 1 goes to y plus 1. And now it's not x plus delta, it is y plus delta. And our direction is direction y. Let's do it again. So copy and paste. And now instead of y plus 1, it's z plus 1. Instead of y plus 1, it's z plus 1. And instead of y plus delta, it is z plus delta. And finally, we'll use our direction z. Okay, so that should give us some vertices. And there we go, 4,138 vertices. Now we can move on to looking for the geometry, or triangles, which is a list of lists of 3 numbers. Each one represents the corner of a triangle. And together, all of these triangles will make up our isosurface. The isosurface will separate all the values within the volume that are above the level from those that are below the level, which is a binary result. And given that we need to evaluate this at the corner of a cube, and a cube has 8 corners, that gives us 2 to the power 8, or 256 possible configurations, or whether or not the volume is above or below the level in the cube. And we can assign a type to each cube of the volume, or each Martian cube, by considering each of its corners in a predefined order. So if we start with a type of 0, if the volume at x, y, and z is greater than or equal to the level, we will add 1. Then looking at x plus 1, y and z, if that is greater than the level, we can add 2. Then we'll go to x plus 1, y plus 1, z, and then add 4. Then with x, y plus 1 and z, we will add 8 if that is above the level. And then we can go around the top of our cube and repeat for all of the same order, but with z plus 1, increasing the amount we add by a power of 2 every single time. So let's calculate the volume type. So we'll start off with our volume type equals 0, and then if the volume test at x, y, and z is true, then we will volume type, and we will OR equals it with 1, which we'll write as 1 shifted 0 times. And then we can copy this and paste it, but now with x plus 1, and now 2, which is 1 shifted 1 time. And now with x plus 1 and y plus 1, but with 1 shifted twice. And now with just y plus 1, 1 shifted 3 times, which is 8. And now we've done all the values on the bottom of the cube, we can copy this and paste it, and we'll swap z to z plus 1, and we'll go 1 shifted 4 times, z plus 1, 1 shifted 5 times, z plus 1, 1 shifted 6 times, z plus 1, 1 shifted 7 times. We have a simplified problem that instead of finding the whole isosurface, we can just find the surface for each of our unit cubes and then combine them. But we still need this geometry for each of the 256 types that we've just calculated. There is a lot of duplication in the 256 configurations due to the symmetry. For example, when there is a value at just one of our corners which is above the level, or the value at just one corner is below the level, then the geometry we need is a single triangle around that corner that was the odd one out. Now, each of these single triangles is identical by rotation operations. And in fact, there's only 15 different configurations of the cubes when symmetry is taken into consideration. Now, within discussions of Martian cubes, and particularly when finding out the geometry that we need in the first place, this is really, really important. But it's really important to note that the actual Martian cubes algorithm itself doesn't exploit any symmetry. And instead, we're going to take our calculated volume type and look up each of the 256 cases in a pre-calculated lookup table. It is possible to calculate this information by hand, and if you're interested in this challenge, I would recommend starting with 2D Marching Squares version of the algorithm, because then there's only 16 different options. But here we're going to use a pre-calculated lookup table that we know is to good quality. I have a file called the Lorentz lookup table.py that contains the geometry information that we need. Opening it, we can see the main content is a list with 256 elements, each comprising a list of 12 numbers that describe the geometry. The 12 numbers are actually 4 sets of 3 numbers, with each of our 3 numbers describing the corner of a triangle. The numbers themselves refer to 2 different lookup tables, the edge delta and edge direction, that will allow us to calculate the vertex ID to reference the numbers that we calculated just now. The edge IDs are constructed from the x, y, and z coordinates and direction. And these tables allow us to find which edge it is relative to our current x, y, and z position. So for edges 0, 3, and 8, well, they're the ones at x, y, and z in the 3 different x, y, and z directions. Edges 1 and 9 will have their IDs given at x plus 1 now, y and z, with the directions y and z. Edges 2 and 11 will have IDs given at x, y plus 1, and z, with directions x and z. Edges 4 and 7 will have their IDs given at x, y, and z plus 1, with directions x and y. Edge 5 will have its ID at x plus 1, y, z plus 1, with a direction y. Edge 6 will have its ID given at x, y plus 1, z plus 1, with a direction x. And finally, edge 10 will have an ID at x plus 1, y plus 1, z, with direction z. Switching back, let's import the information from this file. So from Lawrenson lookup table, import the geometry, and then our edge delta and edge direction. And we can also import direction x, y, and z that are also defined in that file, and when we delete the ones that we defined. We can look up the geometry. We'll load the lookup value equals geometry lookup at volume type. Now let's have a quick look back at this table. We'll see that there are a lot of negative ones, and this represents null or an absence of geometry. So what we can do is we'll enumerate for I in range 0, the length of our lookup in steps of 3, remembering we need 3 points for a triangle. But if the lookup at I is less than 0, then it's a negative 1, and we don't need any geometry, and we can break the loop. So let's take this opportunity to find out the first instance of some geometry. We'll print it out and then see what that looks like. So we can see that this includes 3 edge numbers that we need to use to make a triangle. We can collect the edge numbers in edge 0, edge 1, and edge 2 that we can get by slicing lookup from I to I plus 3. And now we need a function that will convert our edges to vertex IDs. So vertex ID 0 equals, we can call it edge to vertex ID, and that will take our edge 0. We'll define edge to vertex ID, this time within the loop. And this takes an edge number. And we'll use that edge number to load our deltas from the table and the directions. So our deltas, dx, dy, and dz, our edge delta at the edge number, and our direction is the edge direction at the edge number. And then we can use the function we had before, so we'll return our calculate vertex ID, but now at x plus dx, y plus dy, and z plus dz using the direction. And we can repeat this for the other edges, so we can copy and paste using edge 1 and edge 2. That will give us vertex ID 1 and 2. Now we've got these IDs, but they aren't actually the triangles we need. So instead we'll store them in a triangle IDs list. We go to the top of our function. We can initialize triangle IDs to an empty list. And then we can write triangle IDs.append vertex ID 0, 1, and 2. These triangle IDs aren't the triangle information that we need yet, but if we just swap triangles to triangle IDs, we can see how we're getting on. And along with our 4,138 vertices, we've found 8,244 triangles. So the final thing to do is to convert our IDs to indexes. So the IDs that we use depend on the size of the volume, which our graphics software doesn't really care about, and instead it uses IDs that reference the order of each vertex within the vertices list. So we can convert the IDs to indices by creating a dictionary called order of IDs that we can get using dictionary comprehension. So we'll need the order and ID. We want to map the ID onto the order for the order and the ID that we get from enumerating our vertex IDs list. Now to do the conversion, for each of the triangle corners in the triangle IDs, we can triangles.append extra brackets, and then we'll convert. We need to look up in the order of IDs dictionary C, where we can get C for each C in our triangle corners. Now we have the triangles that we needed. And running the program, we see that we get the same number of triangles, but now we've got the right ordering or the right IDs within that set. Okay, so that's all well and good, but let's compare our implementation of Marching cubes with a different implementation that's within the sci-kit image, also known as skimage. So if we import skimage, the skimage.measure has a function called marching cubes. That takes volume, same as ours, and a level, same as ours. We're going to use the method which is called _Lorentz. And that will return us some vertices, we'll call them SK, and triangles SK. And let's copy and paste the print statement, but instead of marching, we're using skimage. And now we've got the vertices SK and triangles SK. So we'll run the code. And, well, that's a great start. We've got the same number of vertices and triangles as skimage. But maybe we can apply a little bit more scrutiny than that. We'll print a blank line, and then maybe we'll look at the first 10 values. So we'll print the vertices up until the 10th one. We'll do that for ours and the vertices SK. Well, the first thing we notice is that we've got a Python list, but skimage returned a NumPy array. So we can do a conversion using the .toList method. Now, well, what we'll see is that we don't have the same numbers at all. But what we've got to remember is that the order of the vertices didn't matter. So to compare them properly, we can do a vertices.sort and a vertices.sk.sort. And then finally, we'll have a look at the numbers. Well, there we go. We have a match between the two. The only difference being that our values contain a mixture of the interpolated floats and the enumerated ints, whereas the skimmage version are arguably nicer being all floats. However, in this case, it doesn't matter. Let's try reducing the level. This should give us a very much bigger volume, being a lower level. And well, we have a key error. Now, the only time we used a dictionary, which would generate a key error, was to convert the triangles. So it seems that we're missing some triangle IDs. So when we enumerated the volume until dim -1 for the marching cubes, this actually results in ignoring any of the vertices that lie on the 3 outer faces. We still need our -1 checks, but we're going to have to remove those. So deleting the dim -1s from our loop, we can go if x is less than dim x-1 and the volume test, etc., etc. We can do that also for the y and for the z. And from now on, none of these calculations make any sense outside of our dim x-1 ranges, so we'll copy and paste these limits here. So now just checking if x is equal to dim x-1, etc. And we'll just continue the loop for y and for z. Okay, so now, let's run the code. And we can see that the key error does not occur. And we have, we do have a much bigger isosurface. Now we've got 44,000 vertices and 87,000 triangles. But again, the same number between us and skimmage. Now, the main point of this is to visualize the data. So we'll highlight and indent the code. Whoops. And for this particular data, we need a level at 0.05. We also need the negative, so minus 0.05. And then we could do 0.005 and minus 0.005 as well. And then we'll export this so we can load it in a graphics program. So we can use the numpy.savez or savezipped function, and we'll call this, we'll just save it quickly in /tmp/marching_level.npz. And this method takes keyword arguments. So vertices equals vertices, triangles equals triangles. Oops. And then the same for our SK values as well. So if we run this code, this should go through and output each of the different geometries at the different levels. So there we go, we've already done that one, that's a good match. And this time at minus 0.05, well, that's also a good match. 0.0005, yep, no key error. And then finally the negative version of that. Again, we have the same number of vertices and triangles. Okay, so There are many options for viewing this geometry information, but we are going to use Blender because Blender is free, Blender is powerful, and it has really great integration with Python. If we load up Blender and perform the customary default cube deletion, at the top you should see a scripting tab, and we'll change the biggest window to the 3D viewport so that we can see what's going on. And we can swap this one up here for back to the text editor. But the main thing we're interested to is this sort of Python built-in interactive console. So let's import NumPy, and NumPy.version.version shows us we've got the same version, which is good, and we can load our data. So we'll remember our levels were 0.05, etc. And we'll load the data into a dictionary, and then we can go for level in levels, and then the data at that level equals numpy.load, and our temp file was /temp/ marching underscore in an f string level. .npz, and now we can see we have our data loaded. Blender stores data in meshes, so to create a new mesh we can use the BPY. That's a module built into the Blender Python which allows you to interact with all aspects of the geometry and most of the program. And the information is stored in the bpy.data, and in this case we want meshes. And we want to create a new mesh, so we can do meshes.new, and that takes one argument, which is the name, and we'll call it 0.05. Now if we look on the right hand side in this little meshes drop down, we should see our new mesh. And if we go back to the console and type in mesh.from and then tab that out, we can see that there's a function called mesh.from_pydata that takes vertices, edges, and faces. Now we have the vertices, and faces are our triangles, and we can see that Blender tells us that if the edges is empty, then Blender will calculate these for us. So let's load the data 0.05 vertices, an empty list of edges, and then data 0.05 and triangles. And now to view this data, Blender needs to associate that mesh with an object, and we can do that just by dragging the mesh into the viewport. And there we go. We can see some nice mesh. When you drag things into the viewport, it will have an arbitrary origin, so let's just zero those out. And let's have a new material that's will color to be red. Oops, that's alpha 0 at red. And that looks nice. Let's repeat the process, but this time we'll create a new mesh called 0.05 skimmage. And the data was the vertices.sk and their triangles sk. We can drag that in, zero our origin, and we can see there's a really good match between the two, and drag it around a little bit, it's perfect overlap, and so our meshes are exactly the same. Very good. Now for this data, I mentioned that we also need our negative values, so let's load those ones up. This time we need the data a mesh, we'll call that negative 0.05, and we need the data that was in 0.05. We'll drag that in, set the origin to 0, and we'll have materials, new, and we'll make this one blue. Very good. We can see a nice surface, much nicer than all of those points. Let's load the mesh that we got from 0.005. We'll just repeat the process. We can drag it in and set the origin to 0. You can see that this completely envelops the red surface because the level is much lower, so therefore our surface is much bigger. And the most important feature, these massive holes, and that's where the level crosses the boundary of our volume. So our surface goes outside the volume, and those were the holes being on that outer surface that caused the key error. And we can admire the final data, and this is the isosurface that we saw at the start of the video in my animations, and we can use it with all of Blender's powerful different features. Now, it's important that this is a relatively basic implementation of Lorenzon's original Martian cubes algorithm. When working with complex sets of data, there can be ambiguity owing to being multiple solutions for some of the examples in our lookup table. And this has been addressed in, for example, Luna's improvement. There are also other different ways of calculating isosurfaces, including Martian tetrahedra. That was created to get around the now expired patent on Martian cubes. There's also dual contouring, which is related but different. And there are many advanced versions of Martian cube, including ones that are adaptive. In fact, there's much work in this area precisely because of the importance of visualizing volume data. So, in summary, we've created a basic implementation of the Martian cubes algorithm in Python. It generates an isosurface from volume data. We compare the volume to a level and then march through each unit cube within the volume, defined by each of the adjacent data points. We looked for all the cases where the volume crossed a predefined level and created a vertex at that point, which we found by linear interpolation. And we also generated a vertex ID for that vertex. We assigned each unit cube a type that was used to access a known geometry lookup table to find various triangles to connect the vertices together. Overall, our algorithm works well, and there's a match between our implementation and the implementation found in the sci-kit image package. But this is only the first part of the story. In the next video in this series, we will look at how we can convert most of these operations to methods on NumPy arrays, and this will give us a substantial speed up in code execution. I hope you found this interesting and informative. Thank you for watching.